Today we're going to look at two different types of specific sequences. The first type is what we call an arithmetic sequence. An arithmetic sequence is when you add or subtract a number each time to get to each term in the sequence. So we call that arithmetic. Now, if you see that a sequence is arithmetic, so for example, 1, 3, 5, 7, I add 2 each time to get to the next term, you can use the following formula to write a rule how to find any term in that sequence. So in other words, an explicit rule. Now, in order to write this rule, you need to have a couple things from the problem. The first thing you need to have is the first term of that specific sequence. So that would be a sub 1. The second thing you need to know is the common difference. Now, there is a trick to find out if a sequence is arithmetic every single time. If you have a common difference, you should see that when you take the second term and subtract the first term, you get the same thing each time. Now, if you do a3 minus a2, it should also equal that common difference. So note how in my problem, if I took the second term and subtracted the first, I got 2. And then if I did 5 minus 3, I also get 2. That means my common difference is that value of 2 for this specific example that I came up with. Now, if you look at the second type of sequence we're going to deal with today, I'm trying to make a joke, but I got nothing. You're going to see that the second type is geometric. Geometric go hand in hand with exponential functions. You will notice that a geometric sequence is created when you have what we call a common ratio, which means we multiply or technically divide by the same number each time. Now, you will notice that when you are working with geometric sequences, this right here is an exponential function. Notice how when you're dealing with arithmetic, you are creating a linear function. Now, if I were to give you an example of a geometric sequence, this would be something like 2, 4, 8, 16, where you multiply by 2 to get to each term. Now, just like with common differences, there's a little trick. If you take a 2 and divide it by a 1, you should be able to get that common ratio. That is the same thing you should get if you take a 3 and divide it by a 2. So the whole idea is if you take the term, the third term and divide it by the second, you're getting the same ratio as the second divided by the first, and so on and so forth. So we call that number that common ratio if it is in fact geometric. And then you will set up that exponential equation to write that sequence. So let's look at a couple examples with arithmetic, a couple with geometric, and then some application of this. So starting with this first one, it says, what is the common difference? So a lot of times we can see this right away. If you notice, I am adding 3, and you need to check to make sure this is true of all terms. Adding 3, adding 3. If so, this is arithmetic and it has this common difference of 3. Now, if you are asked to find the 10th term, you could keep this process going and you can keep going from here. And you can take the 7, we can add 3, the next number would be 10, then 13, 16, 19, let's see what term this is. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and if I add 3 one more time, that gives me 22. So you can definitely do this by hand if you don't have to go too far. But if I said find the 50th term, this would not be fun. And that's why we have these different rules. Now, before we get into the new formulas that I just showed you, when I ask you to write a recursive formula, think about the first day of notes. We can do this even without these new formulas. If I said write the recursive rule, you would need to tell me what is that first term, and then you would need to tell me that a sub n equals, and then remember for recursive, you need to have that a sub n minus 1. Now, think about what do I do to the second term to get to the third term? What do I do to the third term to get to the fourth term? Every single time I take the previous term and I add 3 to it. So writing the recursive rule has not changed. That is still the same. What is going to be different for today's notes is when you're asked to write an explicit formula. If this is arithmetic, I hate it when it does this. It won't let me write. Hold on. Let's do this again. All these things are open. Oh my gosh, what did I do? Let's try this again. All right, of course. It wouldn't be notes with Mrs. Schmer if this didn't happen. Writing an explicit rule, we are going to do the a sub n equals. Now, what you need to know is the first term, which is -5. So that's your a sub 1. Then you're going to put plus, and then sometimes you'll see this formula written 2 different ways. Sometimes people put the common difference at the back. Sometimes they put it in the front. Doesn't matter. But what you're going to say is n minus 1 times the common difference that we just found, which in this case is 3. Now, technically this is the rule, but let's simplify this. I can distribute this 3, and what I'll get is -5 plus 3n minus 3, and then when I simplify, I get my rule of 3n minus 8. So note, a linear function because it is in fact arithmetic. Now, going back to question part B, if you wanted to test to see if our rule was correct, notice if you wanted to find the 10th term, you would sub in a 10 to this rule, and note that if I found a sub 10, I would get 30 minus 8, which equals 22, and that's exactly what we got in part B. So it's a great way to confirm what we found. So that is how you go about answering these questions. Now, if you look at question 2, you're going to get thrown off because you're seeing natural log in the problem. And if I said, what's the common difference? I'd be like, wait, what? Huh? What you talking about? Willis or fool? I don't know. So remember what I taught you guys about this little trick. If it's not obvious to you, take the second term and subtract the first. So if I take natural log 9 and I subtract natural log 3, I should get the same thing as if I subtract natural log 27 with natural log 9. Well, let's think back to the exponential unit and log unit. Remember that when you subtract 2 logs, that's the quotient property. This can be rewritten as the natural log of 9 divided by 3, which equals the natural log of 3. Well, let's see if I get that this time around. If I do the natural log of 27 minus the natural log of 9, that's the natural log of 27 over 9, which is also the natural log of 3. That means that I'm getting the same value each time, and that would represent my common ratio. So note that that means that if I take the natural log 3 and I multiply it by the natural log 3, I get the natural log 9. Note that if I do that here, natural log 3. Now, you may say, well, wait, how is that working? Remember that when you take these common, I don't know if I said multiply, I meant add, because it's a common difference. But note that if you take natural log 3 plus natural log 3, remember the product property that says if you have the sum of 2 logs, it becomes the product of the arguments. And so you're seeing that that does get you to that next natural log. And then if I do natural log 9 plus natural log 3, note that the product of those two is natural log 27. And then if I do it one more time, you're going to see that that is going to give me the natural log of 81. So definitely a unique example, but we're getting as our common difference the natural log 3. Now, for the 10th term, one way you can think about this is ignoring everything I have taught you in today's notes. Even if you just look for patterns here, I'm going to erase this work down here. Even if you just look for patterns, notice that the first term, so this is when n equals 1, is 3, natural log 3. The second term is natural log 3 squared. The third term is the natural log of 3 cubed. So if I said find the 10th term when n equals 10, think about the pattern here and how the n value is the power on the argument value. This 10th term would actually just be the natural log of 3 to the 10th power. Or if you want to think about the properties, remember, move it back, daddy-o. You could do that 10 times the natural log 3. You don't have to find the decimal approximation, but I just want you guys to see that you can identify that pattern within the terms, and that'll help you to find that 10th term. Now, obviously, I want you guys to practice using these formulas. So if I said write a recursive formula, remember you have to tell me what the first term is. And you need to think about, what am I doing to the first term to get to the second term? What am I doing to the second term to get to the third term? And notice that you're taking the previous term and you're adding that common difference of the natural log 3. I always leave a lot of space just in case you have to put something in front of the a sub n minus 1, but that's for geometric. And then finally, writing your explicit rules. Now, don't freak out that we're dealing with natural log here. You're still going to do a sub n equals. You're going to write the first term, which was the natural log 3, and then note that for the n minus 1, we're going to put that in parentheses, and then the common difference we said was the natural log 3. Now, if you simplify this by distributing that natural log 3, you get the natural log 3 plus n times the natural log 3 minus the natural log 3. And I likey what I see. We can get rid of those. And what you get for your explicit rule is n times the natural log 3. Now check it. This should work for any of your terms. Specifically, let's check the 10th term. If I sub in a 10, that is exactly what we got for part B. So note that if you check any other term that's not the 10th term, if I were to check the 4th term, notice that if I put in a 4 for n and I bring that back, Daddy-o, I get 3 to the 4th power, or 81, which was the 4th term there. So that is how you deal with arithmetic. On the next page, we're going to be dealing with some geometric, and then there is that application that I was talking about at the bottom. So moving on to question 3. On question 3, you are asked about common ratios. What am I multiplying by each time? So note that I'm multiplying by 3, by 3, by 3. That pattern continues. That is my common ratio. Now, if that wasn't obvious to you, you could take the second term divided by the first, third term divided by the second, and you would get that value. Now, if I want to do this without any rules or formulas, what I can do is I can take the 54 and I can multiply that by 3 again. So again, this is if you know no patterns and you just see that it's multiplying by 3, you can get that the next term was 162. I can multiply that by 3 and get the next term is 486. I want to find the 8th term, right? So that's 5, 6. This would be 7. And then the 8th term, times 3, is the 4,374. So that would be our answer right here. I kind of like showing you guys how to find it by hand and then showing that our formula does in fact confirm that answer. So if you're asked to now write a recursive formula, remember for recursive, you have to say that first term, and then you have to have that a sub n equals, and we need that a sub n minus 1. Now, what do I do to the second term to get to the third? What do I do to the third to get to the fourth? Oh yeah, I just multiply it by 3. So that would be your recursive rule. Now, finally, your explicit rule, you're going to be using this new formula. We basically want to create an exponential function, and it makes sense when you think about exponential functions, what we're seeing here. You're going to write the initial term, 2, times the growth factor, if you think about that. Now, when you look at the formula, you're going to see that it's represented with that r, that ratio. But in this case, that ratio, what we're multiplying by each time is 3. And then we're going to put n minus 1. Now, you may say, Schmeerbeer, why the n minus 1? Why can't it just be 3 to the nth? Well, think about if I sub in a 1, I should get 2. I need to get a 0 exponent when I sub in a 1, so then I get this initial value of 2. So it needs to be n minus 1 if you want to get that first term. Now, if you want to check to see if our formula works, we can now sub an 8. So notice you're really only multiplying by that ratio 7 times, and then you get that term, that 8th term, as we had expected. So the next problem is another one. Well, let's just wait so I can do this again. I'm sure there's a reason this is happening, and I'm sure you guys are probably sitting there like, oh, how does she not know it's because of this? So I apologize for that. So with this next one, again, this idea of a common ratio, looking to see what am I multiplying by each time. Now, if you don't see it, remember to take the second term and divide it by the first. And note that when I subtract those exponents, I'm getting 2 to the third. You can leave that as 2 to the third, or you can write it as 8. Personally, just because this is all base 2, I'm going to leave it as 2 to the third and make sure it works. If I take the next term and I multiply, so that's 2 to the third. If I multiply by 2 to the third, oh yeah, I am going to add and get the 12. And then if I do that again, I'm going to get that 2 to the 15th. And then you can keep going. If you want to find that 8th term, well, let's keep going. So this is 1, this is 2, 3, 4. So I have to do this 4 more times. So then I'm going to get 2 to the 18th, right? Because I'm just adding 3with the exponent. And then I'm going to get 2 to the 21st. And then I'm going to get 2 to the 24th, 2 to the 27th, right? Did I get 5, 6, 7, 8? So doing that by hand, I'm getting 2 to the 27th power, my salary. No. Write a recursive formula. So when you're writing this recursive formula, we're going to say a sub 1 equals 2 to the 6th. And then we're going to say that a sub n equals, remember we need that a sub n minus 1, so that means the previous term, and we're taking that previous term and multiplying it by 2 to the third each time. Now, finally, to write the explicit formula, we're going to do a sub n equals, remember that we need to take our first term. Oh, come on, I give up. I have a meeting at 2, so I'm trying to get through this. I think I'm going to have to do another video for the last couple of questions on here. So for a sub n equals, remember we want to take that first term, which was 2 to the 6th, and then we're going to add to it n minus 1 times the common difference. Remember we said the common difference was 2 to, I'm sorry, oh my goodness. Sorry. This is common ratio. This is exponential. I apologize for that. I was using the wrong formula. Shows you it's an easy mistake. Honestly, I want to stop this video, but since I've already invested so much time, because this is geometric, we're going to do a sub n equals the first term, which we said was 2 to the 6th. And then in the parentheses, we're going to put our common ratio, 2 to the third. And then remember, we're going to have that n minus 1. Remember that when we sub in a 1, we should get that first term of 2 to the 6th. Now, if you want to simplify this, this is something that definitely can be simplified. If you think about this as 2 to the 6th times 2 to the 3n minus 3. And then if you remember, same base, we can add these exponents. I get 2 to the 3n plus 3 as my rule for this problem. Cool thing is we can check the 8th term. If you sub in an 8 here, notice that you're going to get 3 times 8, 24, plus 3, 27. You get that answer that we got for part B. So what I want you guys to do is look at the next 2 questions, and I would like for you to try them out, see if you can figure out what to do before I teach that to you. When you're ready to look at the next 2, please watch the next video that I have posted.